Okay, someone is the host now. Songoro is the host.
Yeah. So I think we can proceed. Sangora, in case you're speaking, you're muted.
Songoro record.
Did you get a notification that it's recording?
Yeah, it is
Not
recording
yet.
now.
Is it recording?
Yeah. Like
Okay.
I'm also even
Okay.
recording on my side, so I think we can proceed. I'll just share my screen again. Okay, so as we're proceeding from where we stopped, we're going to cover these three things when it comes to statistical regression, and then we're going to do geostatistical models, then our INLA. So taking us from the journey of where we started from workshop 1, to just make all of you aware is what we were literally doing with the data that we were being given is trying to visualize and trying to see the information that we get from the data itself. There was no any additional, maybe like I can say additional mathematics or calculations that we were doing so that we can get extra information from the data we were given. For example, when we were doing investigation of distribution and determinants of the disease among specialized population and applicants of the study in the control of the disease. So we can see from the data we were given, like people from all over the place and maybe people who had disease or not having the disease. And what we were doing is just visualizing those information and getting the information from there. So we will be able to know, like, maybe in Tanzania, there is no disease, and maybe in Ghana, there is a disease, something like that. And as we were saying here, so sorry, I'm just removing something. So from the visualization and the descriptive, we call it like descriptive data, and especially visualizing it through maps and maybe through line graph or through bar graph that we were doing earlier. The only answer that we could give is what and where compared to somewhere else, like what was happening in this place compared to the other place. That is the only information we will get. So we'll get maybe there is maybe more infection in this place compared to the other. That's the only information we will get. And so from the first place of us doing more or getting more information is asking ourselves, why do we have to do modeling from the first place? Like, why do we have to do stats and modeling? Even if it's mathematical modeling, it's statistical modeling, or any other kind of modeling that we're all aware of. The answer is, why is somewhere something higher? Like asking ourselves, like, why is malaria more in Tanzania compared to maybe any country in the Europe? What are the like confounding factors or other things that may be contributing for malaria to be more in Tanzania compared to other places? So that is one of the questions that we cannot answer by just displaying, because when we just display with maps as how we're doing, or maybe just bar plots, we'll see the trend of things, but we really can't answer why, like what are the factors that are leading to a place being more compared to the other. So something else is when we want to do predictions where we want to see what will happen maybe in the next 5 years, in the next 6 years. Can we predict in other places if we know only the information in Tanzania? Can we say about what is happening in Zambia, what is happening in other countries? Like, can we really do that? We can't really do that by just doing descriptive analysis. We really have to do the modeling part of it for us to get that information. And this is something we can really talk about due to the fact that we don't have enough data for us to do everything or maybe predict all the places, and maybe we can't collect data from all over the world. So can we do predictions from the small amount of data that we do have? And what if we have some prior knowledge about something? Can we really see the pattern about something? And that's where we do the Bayesian, where we have prior information. We're going to see it Bayesian model in the next slides. But this happens when we just have prior knowledge of something and you want to do more of information on other places. So Bayesian frameworks to incorporating prior beliefs and then updates the posterior. Now that is, after knowing the prior, what next over what we're getting from the modeling perspective. And when we are going to do the predictions, now we're doing now the modeling based on the relationship between the response variables and covariance. If anyone has a question, please pop in, because I can't see if there is a hand on or not. And we are having different way of doing the modeling. So when we started with the descriptive statistics, is we just describe the differences that are existing in the data, but we can't say for sure why region A is higher compared, as how we were saying. We can't really know the confounding factors of why this place is more compared to the other. But when we do the models, now we know that region A maybe differs from region B because of the temperature or the humidity. Like why is sub-Saharan African countries really having more of malaria cases compared to the other? So we're saying what is the contribution of temperature, what is the contribution of humidity to the spread of malaria, because maybe it's those are the conditions which are favoring the mosquito existence, and maybe it's the houses that we're having that are really contributing to the entrance of mosquitoes in the house, something like that. And with the Bayesian, we have like the prior information, as we were saying. Now, with the prior information that we are having, what really can we get out of that compared to other areas? So something like that. And those are like the models that we're going to have, like having the knowledge on how these models are working. That's when we can go to the spatial modeling in the next slides. So now the main aim here is to find the best fits to explain stuffs. Like when we are having the data, we can see like from these plots, we're having different points of data in different ways. Like the one on the one with the red line is us having just different data around the X and Y axis. And then we're trying to see what is the line of best fits, which can really describe the differences between the points that we're having. We're going to see when we're doing the linear regression. And the one on the right is when we're having, we say like categorical responses, like do you have malaria? No. And that's why we are having a lot of maybe lines, points on the 0. And if you have malaria, then you have points on the 1. And we are trying to see how really we can fit the generalized linear model, which we're going to see on the next. So different models here have different assumptions, and we use different data to answer all these informations. So going down to statistical regression models, we're going to describe a few of the models that are laying foundation of what we're going to do next, starting with linear models. So for people who said have knowledge when it comes to regression, probably when you started learning, we started with linear models, where with linear models is a very small expression of an equation y equals to mx plus c. And we use linear models when now our variables follow normal distribution. Those are like very simple data which can follow normal distribution. We just use linear models. And we then with our y, response variable or dependent variable, with our x is explanatory or independent variables. So when we say like a person has malaria, or maybe malaria cases in Tanzania is more, so we are seeing what are the factors which are leading to having more malaria. So it's the houses, the temperature, the humidity. So the houses, temperature, humidity, those are explanatory variables. So those are the ones explaining why do we have more malaria or less malaria in maybe sub-Saharan Africa, where having malaria or not having malaria, or maybe the number of malaria cases that are happening, that is the Y, which is the dependent variable or the response variables. So explaining this with the when we are trying to now plot, we are having the dependent variables as our y and independent variable as our x. So we're having this, maybe if it's the temperature, and So if it's an independent variable is the temperature and dependent is malaria cases. So we are seeing maybe like as how the temperature increases, also malaria cases increases. So we are trying to see what is the line of best fit, which can really explain the increase of temperature leading to the increase of temperature leading to the increase of malaria cases. So maybe from the line of best fit, and when we find slope, I know maybe many of us know maybe slope, the change of y to change of x. So maybe if we get the slope of 2, it means like after every increase of 2, the temperature increases, maybe malaria cases, maybe 1 or 2 malaria cases, depending on the data. And so this is just an explanation of where do we get now when we were saying C is an intercept, where do we get an intercept when we plot? Because when you're trying to deal with data and when you're going to plot these things, you will see exactly where the intercept is. And when we were talking about the slope, how we calculate the slopes and something like that. And when now we are trying y equals to mx plus c, what is the response? And the explanatory variables. Like, for example, here we are trying to see, like from this last plot is how many hours, maybe the more a person takes more hours to train, that's when you get more scores, something like that. And now with the generalized linear models, like why do we change from linear regression to generalized, like the general linear regression to generalized linear regression is what kind of data are you dealing with? Because when we are trying to deal with malaria cases, or maybe in the vector part, when you're trying to collect mosquitoes, those number of mosquitoes you are getting from different places are not always normally distributed. So if your variables are not normally distributed, what else can you do? What kind of models can you apply? That's when we come to generalized linear models. When we have nonlinear data which are not normally distributed, then we use generalized linear models and not just the general linear models. And so what is the difference between just the normal linear models and generalized linear models is what is included in the model. Here we have a link function which interprets maybe what those kind of data are, what really distribution are they following, if it's just Poisson, if it's binomial or something like that. So not going deep into this, but we should all know that most of the times our data is not normally distributed and we have to use generalized linear models to do it. And next is this is a piece of code which we can use to do to write a model in the ARA, where we use GLM as a function, which it is a package called, I think, LME4. But there are various packages that we can use to do normal generalized linear models or just regression models. And this is one of the parts because as Usman is going to come, he's going to introduce us on how we can use the INLA package to also do the normal regression, and maybe why do we maybe prefer sometimes using INLA and not just the normal and CMC method to use when it comes to the regression, but that can come next. And then apart from the variables not being just normally distributed, sometimes we have like multiple forms of errors that can really happen and we cannot control them because some of the things we can control when we are trying to collect data. Maybe we can control the type of houses that we are going to use. We can control maybe we can control the, what can I say? The district or the place we are going to do our experiments. But some things that we cannot control are, for example, the people who are going to collect those mosquitoes and how the preference of them having the number of mosquitoes, like those volunteers who are going to collect the mosquito in the experiments. Because when we are trying to collect mosquitoes, maybe we are collecting from 6 in the evening to 6 a.m. in the morning. And now, when we are trying to choose the people who are going to volunteer that is something we cannot really control because there are studies which are being saying like maybe mosquitoes prefer people of this blood group compared to the other, something like that. So when we're trying to have those things, multiple forms of errors, we just don't use generalized linear models or just linear models. There is something called mixed models. So we are having those random variables, which really we cannot control in the experiments. And those are the ones which are going to being added in the model and not accounted as fixed variables, but random variables. So that's when we are having generalized linear models, which are extensions of the normal linear mixed models that we're having, or maybe linear models, to allow for different distributions. So alternatively, you could use generalized linear models for an extension of generalized, just generalized models that we saw from the beginning. But then something else we just have to note is not all variables can be kept as fixed variables. Some of them are very random, and we account them as random variables in the models because we know exactly those are the things we cannot control. So keeping them as random, it means we're allowing the model to account for those factors in the showing the results at the end of the day. And the last point that models that we can look at today are Bayesian models. And I think these are really important in the spatial modeling that we are going to do because, as we were saying, these models use prior information for us to really account for the information that we don't know right now, but just the few information that we do have, can we really come up with a conclusion about something? So with the Bayesian models, these are statistical frameworks that use Bayes' theorem. And maybe we can all go read about this Bayes' theorem because it's a really important skill that we should be able to have. So these are being used to really update the information that we are having right now. So we're going to have, I think I have a framework here, but really these models are applied when we're having very noisy and when we are having incomplete data. So when we are having like, we want to get an information of all Africa and we have maybe only 10 countries, but how really can we make a conclusion all over the place? That is incompetence of data, or maybe we don't have a certain information, but we know, maybe the incidence of this place is just 5, but we don't know maybe the number of cases and all that other places, other information. How really can we make conclusion when it comes to the modeling part? So, with this is us having a very noisy data, which sometimes can be incomplete and has everything in it. So now we are going to use the Bayesian framework where now we are having the data itself, the incomplete data, or maybe the few data that we're having. We're having a prior information from other places. Maybe the incidence of Tanzania is 8, but we don't have all other information. And then what is the likelihood of the an estimate that you want to have from it, then we're going to use the Bayes theorem to get the posterior distribution. That is like the results, because from this framework, we are trying to see, to estimate like price of different maybe products. But we're having price purchase data of just few things. We're having prior and likelihood information. Maybe it's using Bernoulli likelihood. Then we construct a model to combine all these likelihood data and prior to get the posterior distribution of maybe how the trend of prices or things, how do they go or something like that. And from there, we get now the response of a very clean information out of the framework we are using. Yes. Is someone asking a question? Okay. Okay. So from the Bayesian now, as I was saying, more of the INLA regression model will be spoken by Osman. But then why? Sometimes you can ask yourself why the preference of using INLA, the integrated nested Laplace approximation, compared to the normal GLM, as how I showed that piece of code of using ARA to do the normal regression that maybe we're used of. But with INLA, it is more fast and efficient, because with the MCMC, if anyone has ever heard of this this term, it's more of Monte Carlo. It's like it goes throughout the data to get like from one point to another. Like it takes from step 1 to step 2 to step 3, maybe until maybe 1,000 steps to see what is the best approximation, or maybe a parameter which fits better the data. But when it comes to this INLA, it's like it takes account of like all the data at once, so it's more faster and efficient. But yeah, that will be spoken by Osman to really explain better. But now the piece of code which is changing from the one that we had earlier, it's this from the line of model. We are not using the GLM, but the INLA as the package itself. And we do the summary of the data. So from there, I think I can handle it to back to Osman to proceed with
Yeah.
geostatistical models.
Okay. Thank you so much, Gloria. Can you hear me?
Yes, we
Nice.
can hear you. Do you want to share your screen
Uh,
or I can proceed?
yeah,
Okay.
yeah, I'm going to share it. Yeah.
Okay. I will stop sharing.
Thank you. Hello, everyone. Let me share my screen. Host disable participant screen sharing. Why? Sangoro, can you make me as a host? Because I can't share. I don't know.
So let me allow you to share if I can.
Yeah.
I did allow you to share.
Okay. You can try to share,
Uh,
Osman.
yeah. It's okay now. It's okay. Uh, yeah. Let me do this. Let me make it as presenter mode. Okay. I see my screen.
Yes, we can.
Okay. Let me go. Yeah. So thank you so much. And hello, guys, Kokoda, and others. Yeah. So, so after the talk from Gloria about why we are going to present this part and also describing the different regression model. Here we are going to see the statistical model. So, which is a different one from the regression statistical model because here we are taking into account the space variation of our data. So here is a simple model where we only take into account some variable in order to explain our response variable. So before you see in the GLM and the generalized linear mix model how we describe a model by assuming our response variable is following specific distribution, and here we are making a real practice in predicting malaria incidence by modeling this variable with a binomial distribution. And here is a formula we have n as we are dealing with proportion, which is prevalence presented by P, and n is the number of people tested. So here we use a logit function to link the prevalence P to the linear predictor with beta plus XB. And beta is an intercept, as you already know. X is a matrix of covariable. Yeah. From it for some variable such as AV, next deviation, LST, it means the temperature, access means accessibility to cities. And you can see these variable are spatially distributed. And after that, we want to get something you see in the right, represented in the Africa map, where we have some data point from the prediction model. So after that, we use a model-based geostatistical approach for modeling the prevalence, and we add a special random effect to express the extra variation. So here in the right, you see a plot describing some level of function, which represents the random effects that we are talking about. And in our previous model, we see here in the formula, we add a z variable, which represents this random effect. And we assume that this z is following a multivariate normal distribution with a mean 0 and a covariance sigma, which is very, very important in this kind of modeling. So how we can explain this z new variable? It is called as a covariant matrix between two samples, I and j, uh, which are geographically separated. And what we can observe is if two samples are close together, the value of the spatial random field at their location is likely to be similar. It means that when we are considering the spatial distribution of malaria, if you take, for example, two villages, so if these two villages are very close, so your random effect could not will not change so much between the two villages. But if your villages are so far between them, so you can have a random parameter which can change from one village to another. So, uh, yeah, so as this is a mathematical variable, there are some conditions for this covariant matrix. It should be positive defined and symmetric. Maybe, I don't know, some of them uh, know this term because it is more related to mathematics. Maybe Kokoda also, you remember about matrix and also symmetric matrix and positive define. Okay. Oh, sorry. So there are some common covariance expression of covariant matrix used in this kind of approach. We have the exponential here defined here with this formula. We also have the square exponential, and we have the Matern function, which is here more complicated, but uh, that we use in our modeling part. Don't worry about the formula because it is already programmed in the INLA package. For you, you are only setting up. Yeah, there is a hand raise.
Yes, can I go ahead?
Are you? Yeah, go ahead.
Okay, the previous slide.
Okay, in the previous slide.
Okay, yes, that is point number 2. If two samples are close together,
Yeah,
the value of the spatial random field at their location is likely to be similar.
Yeah.
Yes. So I was trying to there's a map that you had shown of the malaria study that was given.
Yeah.
Now I was trying to understand, for instance, you as Claudia mentioned that you are estimating prevalence by year,
Yeah. Yeah.
prevalence by year, and
Yeah.
then you are using a district.
Yeah.
Okay, so each district, I
Yeah.
would say some issues of uh, distance that is close to each other.
Yeah.
Okay, so by the time you finish the whole country, you
Yeah.
have the issues of interrelationship.
Yeah.
Now, how could that be, especially that you are looking at the country level and then by
Yeah.
district? I don't know if my
Mm.
question is clear.
Uh, yeah. If I understand, you are asking about when you are considering predicting in country level, but you first have district data point.
Yes.
Yeah, it's in this kind of modeling, even if you are predicting in country level or admin one, admin two, some administrative level, you should have initially, for example, your data in health facility level, meaning that in each health facility you have your coordinates. Yeah. Because using coordinates of district, and from coordinates it is calculating the distance between two districts by this formula, where S represents the location, is that you have your coordinate. Coordinate means longitude and latitude. So it means that if you have two districts very close, that the distance is so much. Also, some extra effects that influence the malaria transmission are not changing much. So your random variable is likely to be the same in these two close district.
Okay,
I don't
thank you.
know
So there's
if
no
I.
parameter per se to say if the distance is at this level, you expect similarity. There's no agreed parameter, or it's a random issue depending on, yeah.
Yeah, yeah. So because the randomness come from some external effect, yeah. For example, from one place to another, you can have many variation coming from maybe some demographic aspect, and also maybe some environmental aspects that you are not taking directly account in your variable, but that you know these two places are different. And in order to measure these differences between two places, you consider this random spatial effect.
Thank you.
Yeah. We have another question from others. Okay, good. So, and in our INLA, the most of time we are using this maternal covariance. Okay, this one where we have this very big formula, but as I mentioned, don't care about the formula because you are always using the packets which be you are, are you
You're breaking up, Osman.
Osman?
We can't hear you from this side.
Osman?
I think he is facing internet issue.
Yeah, let me text him.
Maybe he could go and join you again. Cannot.
Ulikuwa na nini? Ulikuja na
Yeah, it is one. Go ahead, no problem.
sorry guys, it was right to my Zoom, I think. I don't know what was happening. So can you hear me now?
Yes, we can hear you.
Yeah, sorry. Yeah. Okay, yeah. Can
What do you need to
you see
mute?
my screen again?
Yeah, we can.
Eh?
We can see.
Okay. So yeah. So why we want our model to be Bayesian? As uh, Gloria mentioned before, the Bayesian allow you prediction, meaning that uh, for the fitting, after the fitting, your parameter are not uh, having one values, but you can have a sample of your parameter. And with this sample of parameter, you can calculate your confidence interval, for example, which is very useful in prediction. And for this version, the main thing is to define first your priors. Your priors, it's your hypothesis before going to the model. For example, you see the linear regression. You have some parameters such as intercept and regression coefficient. When you are using Bayesian for this kind of modeling, you have to consider first, for example, which kind of distribution each each of your regression parameter and intercept also is following, which kind of distribution that calls your priors in the model. So about computational, because these are not very simple to compute model, you need some good yeah, software also and with memory. So this model, maybe there is some alternative mathematical accept like the Gaussian Markov random effect, Fourier feature, but I think you don't care about it. It's related to mathematical aspect. So let me move to the next one. So here we are describing our modeling parts, our modeling practice in use real data. In first, we consider the data from Madagascar, where we are predicting the prevalence. We constituted a mesh, and also SPD. SPD is stochastic partial differential equation. We make data staking. We make the formula in INLA. We fit the model, get the result, make prediction, and do validation. I'm just going to describe the process, and at the end, we go to R to make it practice. Yeah.
All right.
So let me. I don't know how to. Okay, why using INLA? INLA is R package, which is constantly on development, meaning that you have to be aware about changing this package or making new things. And when we are using it, you have to check if the formula, or you have to add some new parameters in the function. So it can be it fits your complex space compared to your GLM or GLM mix, and also it takes into account the space and the time. For example, you are predicting by district, by also months. Take this variational in the same time. It gives you posterior estimate. You are using Bayesian. You consider your priors, the model give you a posterior. And it is accessible in R. I think everyone here is installed the package in R and accessible. So more information about INLA, you can find it via this link. So here are the data. We have the PR data for Madagascar. Uh, uh, is it possible that someone tell me what PR means?
What it is?
PR, yeah?
Yeah. Prevalence rate.
Prevalence rate, yeah?
Yeah.
Okay. Okay. But if you say prevalence is a rate, yeah? Yeah. Kokoda?
Prevalence rate. What I understand.
Yeah, but
Because we have here sample size,
yeah,
which means the number of people sampled, and it obtained this, the number of people tested positive over this sample size. So it is
Yeah.
prevalence rate.
Someone can propose different thing, or you all agreed with Kokoda prevalence rate?
Yes, we agree with Kokoda.
For me, maybe Sangoro will confirm it, or Gloria. For me, if you say prevalence, it's already a rate.
Yes.
Yeah,
So what about parasite rate?
yeah,
What does
I think it is.
PR mean, guys?
Yeah, PR is parasite rate. Yeah,
Yeah, so it is prevalence Plasmodium falciparum.
prevalence plus.
Plasmodium falciparum prevalence rate. It is what
No,
you are.
Kokoda.
No, it is Kokoda.
No prevalence rate.
No, right.
Kokoda, we talked about this last week, man.
It is parasite rate.
Okay. Parasite
Because
rate.
if you say prevalence, you don't have to add rate, yeah? Time, yeah.
Kokoda,
So, yeah, go ahead, Sangoro.
when I come back, Kokoda, we're going to have a quiz, man.
No
We
worry.
talked about this last week. Anyway, yeah, it is parasite rate. So the number of whatever sample size you're measuring, whether it's children under 5, whether it's pregnant women, whether it's the community, the number of people that have parasites out of the total number of people that you're measuring. So it's parasite rate.
Yeah. Okay. So, yeah, in has data, we have this parasite rate from Madagascar. It includes the number of positive and examine it. And we are using the binomial model. And sometimes if you are dealing with different kind of data, the distribution can change. Okay, you are not always using the binomial. For example, if you are using, for example, the cases which are count data, as Gloria mentioned, we can use a different distribution like Poisson or negative binomial. Yeah, that is maybe the first thing that you have to think is which kind of data I have and how I am going to use the right distribution probability.
Okay.
Because if not, if you don't do that in your first and you don't use the adequate distribution, your output, the result will change a lot, and you will have much issues for interpreting the results that you have in final.
Osman?
So here is a formula of
Osman, before you go ahead, there's a question from Christina. Christina,
okay.
do you want to ask the question?
Yeah, I can ask, although I've written on the chat box. I was asking how much of the missingness can affect our predictions? What is the degree of the missingness?
Or how does missing value affect the results of the model, right?
Yeah, I mean how much the missingness of the data, to what degree that this should be the threshold of the missing data, that maybe beyond it can affect our predictions.
Yeah, Kokoda, can you help me, please? I don't hear clearly.
So she's asking about missing data,
Yeah.
missing value. For example, missing value in one of the prevalence we mentioned here.
Yeah.
how much does it affect the results of the model?
Okay,
Okay. Yeah, I understand. So maybe it's more related to the validation of your prediction, because, for example, even if you don't have much data, if you are using the Bayesian framework, it can give you some prediction. So after getting this prediction, you have to compare it with your real data, and the main issues can come from that. How you are going to validate your prediction without getting real observation in many points. That is the main issues about missingness. If you have many data points that are missing, even you get your prediction with the Bayesian framework, you should not make very accurate validation, because you don't know if the value obtained from the prediction is good or is low or is high, due to the missingness of your observation.
Yeah, so Osman, so I think what Christina is also asking is there a threshold of how much missingness you can say that the data is this proportion of the data is missing, so we are unlikely, our predictions are unlikely to be correct.
Yeah. So
Yeah.
a threshold, uh, I don't know exactly if there is a threshold about that, but if you who can believe your data, if, for example, you are predicting in a country and you see in the much important district point, you already have the data from that district, and only some small districts where you don't have data. So uh, for me, you can proceed with your model and get your prediction and make conclusion. But if you don't have data in many important districts, even if you make your prediction, your conclusion will not be more accurate, because you are losing information in very important places. It can depend on you, because it's you who is going to make modeling. And if you are not sure from the data that you have, I think you have to study the completeness of data. There are many uh, models that can help you to deal with the incompleteness of data before thinking of modeling. Yeah.
Yeah,
But
maybe Osman, from
yeah,
my
go ahead.
from my classical model, not from the Bayesian
Yeah,
perspective, is that first you are guided by the sample size
yeah,
that you are using,
yeah,
and if your data meets the threshold of the sample size,
yeah,
meaning you have enough power of the study for you to make any inferences from the outcomes that you are going to make. However, there are also other issues after you've done your sample size, and to what extent should your data be complete. There have been some references of a 20%, at least if 20% is missing, you can go ahead. However, as you have already explained, that there are scenarios that would happen in the field Sometimes you are estimating rare cases, and for some reasons you cannot have sufficient data. And the issue is, does your prediction meet what others also predicted? And you should have a backup, but it shouldn't be a scenario whereby the study has collapsed due to insufficient data and then you proceed to model. Thank you.
Yeah. Good. Thank you, Mwanda. Christina?
Yeah, thank you.
Okay, good. Thank you so much. So here, we consider this model for the malaria prevalence data, and we have the random effect here. It's represented by CS here, and where the S means the location. Okay, in each location we can have an output. CS flow of normal distribution with a mean 0, and covariance sigma, where sigma is the Merton correlation function that we show before. Beta is the intercept, and beta 0 is the intercept, and beta are the slope parameter of our covariates. So this modeling part use something that we called SPD. SPD is stochastic partial differential equation to represent the spatial distribution of our data. So this SPD is used to make mesh. Mesh mean first you have your plot in the left where you have your country space, but you have to transform it to your plot in the right where you have triangles in order to capture every data point in your space. So how to construct this mesh in order to get something that you see in here in this figure? You have to, as I mentioned here, for this packet, there are many functions predefined. Your work will only be to put the right argument of your function, and you run your model. So there are different arguments in our function here. It called INLA.mesh.2D. 2D is the dimension. Yeah. We have the log argument here representing your coordinates, meaning that your in each data point you have your longitude and latitude. I think you remember about the one session about the spatial data where we were talking about coordinate and also projection. So coordinate is longitude and latitude, and also you have another argument, which is your boundary. It is a shapefile of your country. Okay. And you have another argument, max edge here, which takes some values. And this This is related to our triangles. So the largest allowed triangle length, the lower the number, the higher the resolution. It means that for these values, we are going to play with these values in our R practice. You can see how changing this value in this argument can affect our mesh. And also you have an offset. It's it's represent how far you want to extend your domain. Meaning that if you are working with a country here, for example, the blue line can represent the front line of your country, but you can extend the out part of your country in order to consider some variational information from there. And also you have a cutoff argument which can reduce the clustering of your triangles. Okay, good. Okay. After that, after having your mesh, you define your A matrix. Okay. I am describing the process. After that, we are going to to make practice in R. Okay. So after the mesh has been set up, we need to fit INLA and convert this into a model format. It's how you can define your E matrix. And the formula is here. You use the function inla.spd.make.a, where you have has argument the mesh, your location, and you can get your A matrix. And this A matrix create a sparse matrix because you are your data point, and create SPD for a special structure. This is a function that built upon the spatial structure that you assume that you already have your mesh. After that, we have your function SPD here, and you have your EZ, which can create your index, spatial index of your mesh. After that, you have the stack data, where you have the function inla.stack. You can observe that the most of the function start with inla because you are in the inla package. And in this function, you have your response variable y, and you have your number of tested, which is on the sample, and you have your A matrix, and you have your effect, because you have mixed effect coming from your covariates. You have also your random effect coming from your spatial random parameter. And in this model has covariates we are using the elevation, the accessibility to cities, the day temperature, the rainfall, and the AV, index vegetation. After that, we create our formula, we define our formula where we have the Y. I think we already see this formula in the statistical regression models part where we are uh, showing how we can compute, for example, GLM or uh, also linear models. Here, the formula is to assume that Y can be predicted by using an intercept, spatial path defined by function f here, depending on your location, and your different covariates that you take into account. And you call the INLA function here, the INLA function, which take this argument and where you can specify your probability distribution, which is binomial in our case. And after fitting your model, you can check your posterior mean parameters. For example, for the effect, fixed effect parameters, you can have here the coefficient of your different regression parameter of your covariates, and this this also give you the standard deviation, the quantile modes, okay, and the first column here give you the estimated mean of your regression parameter representing the beta in your formula. And also you can check how your parameter are distributed by calling this uh, script, and you can check for each parameter how the density look like. Here you have, for example, the beta parameter. Here you have the beta of access representing the regression coefficient of the variable accessibility to cities. And you can see that all these parameters uh, are following as a normal distribution curve. So it means that if you were making priors, meaning that you were choosing your distribution of your parameter in priori, you can say that each parameter flow on normal distribution that you can specify the mean and the variance. Do you have question for me? After that, also you can check for your hyperparameters. It is as your parameter from your random partial effect. And here you have your theta 1 and theta 2, which are calculated from log tau and log C. Is it a question?
I have a question.
Yeah, go ahead.
So, can you go back to the slide where I distribution of parameters?
Yeah,
The table one.
the previous one.
Yeah, before this. Yeah, this one. So
Yeah.
these are the distribution of the parameter posterior distribution, right?
Yes. Posterior
So
values.
yeah, I was wondering how did you choose the prior, because this is Bayesian framework, right?
Yes.
Yeah, so for Bayesian, you mentioned we have to have the prior
Yes.
for this parameter. Do we also have 12 priors?
Now, for INLA, you are not you don't specify about priors. It is included, and you can only it is included in the function, and after fitting your model, you can check your parameters, and if you see that the output, for example, here, you see the beta is distributed like this with a mean minus, and you have the small variance. If you don't agree this result, it means that you are to think about a model where you can specify your parameters in programming your model.
And another, so for this one, priors are like they are already set up by this.
Yeah, exactly. Yeah.
Okay.
Yeah.
So another question is, if you could go, if you could move to the next slide.
This one?
Yeah, where you have hyperparameters.
Yes.
So I was wondering where did we have this? Or simply what are the hyperparameters?
Yeah.
And how are they different from the other one?
Yeah, these hyperparameters come from the spatial effect.
Spatial field.
Yeah, because in your model you are considering two effects. Fixed effect coming from your covariates.
Random effective from
Yeah.
the. Okay.
Exactly. Yeah. Good.
Yeah, so if I may add, anything that you specify as a random parameter will be modeled as a hyperparameter.
Yes.
Is that correct, Osman? Yeah, and Osman, okay. Christina has a hand up. Christina, yes?
Can you move to the different?
You're gonna use yours. Okay.
Oh.
Yeah, mute yours, then use this one.
Okay. Well, I was asking about, so from the whole procedure, I saw that we created the mesh. Then after, we used the mesh to feed it in the INLA. And then we did the data stacking before the model fitting. So my question was, after feeding the mesh into the INLA, we got the vectors, we got the main list, the main the vectors into the model. And then after we did the data stacking. So I was asking, what was the main objective of data stacking? What were you looking at? What are we expecting to receive? Why did we do the data stacking before fitting the model?
Oh, you are so a bit far from the micro. Kokoda, can you repeat, please, the question?
So can you go to the slide where we are stacking the data before modeling?
Okay. Yeah.
So she's wondering why are we stacking the data before modeling? That's the question.
Yeah. So this is only to organize your data and organize the output of your data. It is it is only related to organization
Okay.
because
So
you make a recap here. In your model, you need your response, your number of sample, your A matrix, and your different effects. That are the different part of your model, yeah?
mm,
And the stack means that you make it in an object.
okay.
Yeah, because your model is going to use this object because you see, for example, here, you have this argument tag, which is an optional, but only for labeling the data stack.
Yeah.
Yeah, yeah.
So,
It's only for organization of your data. You make it in one object named tag, named that. Yeah,
so the function is for modeling is expecting the structure to be like this.
exactly. Yeah,
Uh,
yeah,
that,
yeah. It's only related to the structure of your input. Yeah.
thank you.
Okay. Good. You are welcome.
Osman,
Yeah.
Osman, let me go
Yeah.
ahead. So I'm gonna follow up on Kokoda's question about the priors.
Okay.
So, like you said, the priors are not predefined, but you can tell whether the priors were correctly chosen depending on the output of the fixed, the
Parameter.
hyperparameter.
Yeah. Yeah.
Yeah,
Yeah.
you can tell whether. So, for example, yeah, here.
Yeah.
So let's say these are normal. So if let's say they're not normally distributed, would
Yeah.
you assume that it is the priors that are not correct, or would you assume that it is the data? It is you didn't define your data distribution correctly. So for example,
Yeah.
if you used a negative binomial or a Poisson instead of a binomial distribution or link,
Yeah.
would would the would the plot of the hyperparameters and parameters on and the fixed effects look different?
Yeah.
Of
Yeah.
course, they will look different.
Yeah. Yeah. Yeah.
Yeah,
Yeah. Of course.
they will. So
Yeah.
so if they do look different, would you say that it is the specification of your model? Let's say if you specified it as a Poisson instead of a binomial, or is it is it because you assumed that maybe the distribution is normal while it is not normal?
Yeah. So most of time,
Yeah.
the result of this can come from your distribution of your data that you assume before.
Uh-huh.
And also the parameters are adjusted in order to have the best fit of your real data, yeah?
Yes.
And it means that the model is combining different aspects of your parameter in order to get you the best fit. It's why for INLA, you didn't tell it which distribution that your parameters are following. It organize it internally in order to give you the best fit.
No,
By
you actually don't you specify the in family, don't you specify whether it's binomial? If you go back to your slides, there's a way where you
not
specify.
the specification only come from the data, not the parameter.
Yes. Oh, so
Yeah,
it comes. So that's what I'm saying. So if you specify your data wrongly, then these plots would tell you whether you specified, because they would not look normal or they would be non-normal.
Yeah, no, sure. Yeah, if you first wrongly specify a bad distribution of your data,
Yeah.
you should expect also bad uh, distribution of your parameter. Yeah.
So this is a way of checking whether your specification, whether you specified your data distribution correctly. Yeah.
Yeah, but it's for this, it
Yeah.
means that you already know which kind of distribution that you want that your parameter flow
Okay.
for your parameter. Yeah.
Uh-huh.
If, for example, let's say if I am including in my model the IT and use effect, okay, has covariance.
Mhm.
In this set of covariance, I include my IT and use effect, yeah.
Yes. Yes.
And for with INLA, you didn't tell INLA that the parameter regression of IT and use that I want should be not normal, because with normal you can have negative value.
Yeah.
It should be maybe a truncated normal, meaning that only getting value from 0 to plus
One.
infinity, yeah?
Yeah.
Or maybe a log normal, which give you positive value, yeah?
Mm-hmm.
But in prior, you don't specify that. You only give the a vector of IT and use has covariance. You feed your model and you get a regression coefficient of this parameter, and you can also check the distribution, the posterior distribution of that parameter. Yeah.
Okay. Okay.
Okay.
Yeah.
After getting the posterior distribution, if you see the model gives this parameter have normal distribution, for example, there are some value, negative values there, it it means that the model is not uh, doing a good job for you.
Okay.
Okay, because you already know that the parameters should not be negative, because you consider that for the ITN use you have a negative effect, yeah.
Uh-huh.
So
Yeah.
it means that you should have a positive values in order to make minus beta 5 ITN, yeah, in your formula.
Okay. Yeah. I understand. I think we go on with
Yeah,
the
yeah.
yeah.
It's only related if you already know that the parameters that you want to have should follow a specific distribution. You can think to change maybe the distribution of your value, or to change to a different model, for example, greater or or something different. Yeah,
Okay. Cool.
good. Yeah,
Okay.
no more question.
Yeah.
Okay, here are the distribution, posterior distribution of your hyperparameter. And after fitting your model, you go to the prediction, and there are two ways to make this prediction. In one way is to continue to use the INLA prediction function. It is one option, or to use the formula after getting your uh, regression coefficient. And for for that, you have to prepare your data, meaning that you have to create your reference image of your map. You have to get the point of the where you have data with this, because here you see with this which uh, different NIL get values reference image. It means that you are only taking index where you have data. In each location we have data, not you don't take into account the NA data point. And after that, predicting inside INLA, it means that you have to create your A matrix for a prediction, and you start your data, means that you create an adequate structure, and after that you call the function here in order to predict. You still use the INLA function, but you include more arguments here, like the control predictor, dot predictor, which use some specific argument like link one, and link one is used to connect the unobserved NA values to your family distribution. Because, for example, here you see for the prediction, which is different for the fitting. For the prediction, you don't want to use your real data, yeah, because you are predicting them. That means that your vector of response should be transformed had NA has missing, because you are predicting to get values for this different observation, which is different for the fitting. For the fitting, you use real data, but for the prediction, you transform this part, and you get the covariance and the random effect. So that was prediction in INLA. Okay. Outside INLA, you still create your A matrix of prediction, because after calling this function, you can get after the fitting. When you fit also, you already get your regression parameter, means the intercept. The beta 1 represents the regression parameter of access, beta 2 represents the regression parameter of elevation, beta 3, beta 4. Because you already have access, elevation, AV, LST day values in your folder that are the covariance value. And from the model also, you can get your random effect here by running this two line. And after getting all that component, you can construct your formula here in order to get your prediction. Meaning that if you call model $summary dot fixed, all the fixed are your coverage and the intercept. If you call here intercept, you make the same with the others covariate, and this can give you your predictive values outside the INLA function. Good. After getting your prediction, you think to validate your model because before starting making interpretation or having conclusion, you have to be sure that your models give you reliable values, and before maybe thinking to write paper to publish or to present it in some seminar. So comparison and evaluation is fundamental aspect in statistic data analysis, and how we do it in this kind of modeling. First, you have your data set, you split it into training and testing set. Sometime we take as training set, for example, 80% of our data, and test the rest, meaning that the 20%. But sometimes also in some model, for example, in some machine learning model, you split your data in 3 subset. You have your training, your test, and your validation. I don't know if someone is familiar with this kind of process. For example, Moende, did you use this in your modeling background?
Are you asking a question about?
Yeah, about testing, training, and validation set. Yeah.
Is that a
Yeah,
question?
I have experience of this.
You have experience. Yeah.
Yeah, and it's normally when you want to save amount of data for validation.
Okay. Okay. Thank you.
Sometimes split into 2 parts for
Yeah.
training and testing. In machine learning, up to 3 parts:
Yes.
testing and validation.
Exactly. Exactly. Thank you. Munde, go ahead.
No, I haven't done machine learning.
Okay. Yeah. But in statistical regression, you use a lot training and testing set, yeah? Okay, good. So, in the training means that it's where you are fitting your model to get your parameters. You use the real data in that part. But in the testing set, you make your observation NA because you are not going to use that real data. Okay, you transform it in NA. You conduct your prediction maybe inside INLA or outside INLA in order to get the values of the NA in the test set. And after getting this value in the test set, you can make a comparison of that value predicted to the original value that you already have. And you can make a plot like this, where you you show how the correlation is between the observed and the predicted. And uh, for you, for example, are you happy if your model give you something like that, like this plot?
No,
No, why?
it's supposed to, the friends, they are supposed to like to be close to this linear line.
Uh, yeah,
Yeah, it's
uh,
somehow missing
ye-
the key
exactly.
values.
Yeah, because here you are making like linear models because you are making a linear regression here in this part between the predicted and the observation, and you want your data, your point follows a line, like the first plot that Gloria already show you in the linear regression part. What you want is all your data point following, for example, this line. If you get some models that give you something like that, where your data are flowing online, it means that your model is doing a good job. But here you see there are the data are very dispersed, and it means that this model need to be improved. And the question, what would
So,
you, yeah,
window, go ahead.
no, I'm just asking how you can make improvement to this model.
Maybe you can add more data.
You can add
More data.
more data, yeah? If you have dealing with uh, many missing data, as Christina was asking, yeah?
Yeah, because they want
Okay.
to require a lot of data so that it can capture the
Yeah,
relationship.
including more data. Which kind of data? Is it your observed data or your covariates or to modify your random effect function?
Oh, those are many factors. Maybe you can do either of them or two of them.
Okay.
You can add that data for the covariates or modify the random effect as you said.
Yeah.
Those are my opinions.
Good.
I believe they can improve the performance.
Okay. Okay. Good. Can someone add something?
I just wanted to find out in this model
Yeah.
of spatial data, do you define your intercepts?
Uh, my model here, no.
No.
Your intercept, you can define it, or INLA can add it internally.
Okay.
Yeah. But you
Okay.
can define that vector also.
Okay. I wanted to find the possibility of doing that in order to improve. Yeah.
Yeah. Yeah. It should be also a good way to do about changing the intercept, because the intercept represents values that you have, expected values that you have, if you are not considering any external element. Yeah. Okay. Uh, can you? propose something else? From the DAR, yeah. How we can improve this model?
Christina has a suggestion.
Yeah?
Sarah has something. Christine. Okay, there is no. They say add more data. You have.
I've already posted.
Okay, on the chat you can find the suggestion.
On the chat.
Yeah.
Sangoro, can you read the chat, please, for me?
So Christina says maybe you change your model.
Change your model. What does it mean?
We change the different models.
Go to plan B. Use plan B.
I mean, we consider another model apart from that.
Yeah. So
Maybe the one which Gloria said, was it GLMM or something?
Oh, okay. Okay. Changing your mathematical model, yeah? The statistical model, yeah?
yeah, your statistical model. So
For
for example,
example, if you are working with linear model, you can change to GLM or GLMM or INLA or something, yeah?
yes.
So,
So
Okay.
my last thinking is that since we are in the Bayesian modeling,
Yeah.
we can adjust the priori from the classical model.
Okay. Okay.
I think we have room to adjust the prior.
Okay. Okay.
Just my thinking.
Yes. It's possible, yeah. It's possible you make hypothesis from your regression coefficient that you want to have in as posterior, yeah. For example, if you already know that for example covariates a specific covariate should have a positive regression coefficient, you can think to define it in prior. Example, making conditions that the model that I want is to give a regression parameter of this specific covariate to be positive. Yeah. Yeah. Good. So that is the entire process about modeling. You have your real data. You think your kind of model. You set up your model. You get the parameter. You check your parameter. You get the prediction. You make validation. You compare, and you do your interpretation. Sometimes you can do this work many times before having your final conclusion. Yeah. Good.
so
Yeah. Go
So
ahead.
this process of splitting data into groups of testing and training, it's no longer happened before fitting the model, right?
No.
So if you have to do this after fitting the model,
Yeah.
where are you going to get the data for the validation? Because what I know is
Yeah. But
they have to be new data, which the model never saw it before, to avoid the leakage. Or it was different.
yeah, if you want to validate, so you have to get new data. But how if you are working with malaria, for example, you want your model, you can go to the person who already provided you the data before, ask him, have you new data for this new year? If they have, they can share you and you can um,
Validate.
validate your model. Yeah.
Wait,
Uh,
so another way is if you split your data into training and test. So
Yeah.
you use 80% of your data to train,
Yeah.
yeah? Do you understand, Kokoda? So 80% of your data to train.
yeah.
And then when you test the model, you use the test data that the model has not seen before.
Okay.
Yeah, so that's a form of validation. So you train. So let's say you have what 3,000 data points. You can split it
Yeah.
into 20. So you can split your data into 2,500, and you train your data using those data points. And then when you come to test your data, you use the 500 data points that were not used to train the model.
Which means
Yeah.
the process has to occur at the beginning before fitting, right?
No. Validation is kind of, how can I say, it's kind of a different process from prediction. So
Yeah.
validation is just to show is your does your model does it predict how much does it predict your data correctly?
Yeah.
I don't know if
Yeah.
we understand each other. Osman, I don't know if yeah.
Yeah. Yeah. You are right. It means that, for example, if you have a model, because your model has a formula, yeah, for example, and in your formula, you say that your model is partially and temporally distributed. So if you have your data for one period and you split it in training and test it, you finish. But in your formula, you have a temporal variation. Yeah, meaning that if for your model, if you can get value, if you can change the time, you can get a new prediction. So, but for this new time, you don't have data in your data set. So your model can give you a new values, but to validate, to be sure that the new value that your model give is reliable or not, you have to get an observed value from where you get your original values, and you compare these two values. It's it's mean validation, yeah. Kokoda?
Have you
Yeah.
have you
Yeah. Yeah.
yeah have you
Okay,
understood,
so
Kokoda?
good. Thank you. It's interesting, yeah. And as you see, our INLA model has some limitation. Uh, it is not using the Gaussian. Uh, no Gaussian data don't fit as well, and not all diagnostic work. It's not flexible for more complex spatial models, meaning that joining model and combination of aerial and point data. For that, you can use different one named TMB, template model builder, which is more sophisticated for INLA. And also it doesn't work without standardizing the link. So there are here some references that you can explore to more understand about spatial modeling and also R INLA. If there are no, yeah,
There is a question.
okay, go ahead.
Also, I am asking about we usually see that people first do maybe a regression analysis and then select the covariates.
I can't hear you well.
Can you hear me now?
Yeah, good, yeah.
Yeah, we usually see that people, other studies, they will do a logistic regression and then select the variables from there. So would that have helped in this case?
For making the selection variables?
Yeah, so that the model would be fitting.
Yeah, it was the question in the validation part because we asked how we can improve this model, and that could be a good thing about putting all your covariates in your model. You can make a pre-work about selecting the most important covariates to your response variable before fitting your model.
Okay, thank you.
Yeah. It is a pre-work of if you can do it if you, for example, you have more than 4, 5, 6, or more than covariates. So, but when you check, for example, the correlation between each covariate to your response, you see that some of them have very low correlation, and this means that if you run your model with all these bad covariates, you are only increasing your computational, and also you can have a surprising is uh, er, no, not error, but surprising output results about the multicollinearity of your covariates.
Okay.
Meaning that, yeah, also, for example, let's consider, for example, two covariates in a set. So, but what you want is each covariate make an effect to your response variable y. But the problem is if you don't check about correlation, also uh, making the selection variable, you can have the covariate one is only explaining or affecting the covariate 2, but not the response variable. It means that you have a multicollinearity problem, and this is not very good for your model.
So it is like a confounder.
Yeah. Yeah, you have to remove them. Yeah.
It is like a confounder.
Co-founder. Yeah, exactly. Yeah.
Thank you.
Yeah, you have to explore. You have to explore that before including it in your model. Yeah.
Okay.
Okay, guys, we are going to take a 5-minute break. But just before
Yeah.
that, regarding the logistic regression of selecting covariates that you asked about, Harriet, there's some cases where you'll find that if you did a logistic regression and maybe try to define the relationship between prevalence and the covariate, let's say at times you might find that there's no the logistic regression shows there's no relationship between the response variable and actually the explanatory variables. But in actual fact,
Yeah.
we know that there is a relationship. So in such cases, it depends on your well, how can I say? This is subjective. You can choose to put it into the model. Just because you know that there is actually an actual relationship between malaria and rain and malaria and temperature and stuff like that. So the
Yeah.
cases like that.
Okay.
Correct,
Yeah.
Oscar?
Yes. So if there are no more questions, we can go to our practice time.
Before we do that, Osman, can we give them like 4-minute break and then we come back?
Well, I think 4 is short, maybe 6.
Okay, so we come back at
Yes,
12.
6 or 7 is good.
Yeah, 6 or 7. Yeah, good.
We come back at 12:15.
Sagoro,
Yes.
I need your help during this break. I don't know, either you or Grodia. I think it's Grodia who was in that class. I missed I tried to follow the notes. I was asking for the video. Unfortunately, the video was not given to us. There were some few technicalities I think Juniper explained. So I'll need your short help on the fork and clone, so that I do the required GitHub repository for Osman.
Do you have a GitHub account?
Yes.
So I think the easiest way is just go to the link that Juniper sent. It's in the email. So Osman's repo, and then click on that link. Try sharing your screen. You see?
Okay. Let me share screen. Okay, let me go to the email first, and then I share. I open the email and then I share. Okay, let me share now. Okay, there we go. It should be this one. Excuse me. Okay, are you able to see?
It's not okay. Yeah. So click on Osman's GitHub repo.
Here.
And then you see, where is fork? Can you see fork on your right?
On my right.
Fork, where it's written fork
Is where
9.
there's code. Are you seeing where there's code here?
No, fork 9. Just on the top, below sign in.
Okay, it should be this side where the zoom up is, maybe. Yes, here.
Okay, yes. Click fork. And then so that's your GitHub. Yeah, sign in. Okay. It should take you there. So where's your, is it signing in? Should be your GitHub now.
I think
Okay, look.
so. Yes, here.
Is this you? This looks like Osman. ODI 1990.
Huh? AMM.
No. I'm saying we still look like we're in Osman's repo, because Osman is ODI, OD 1992. So we need to get into your GitHub. Can you get into your GitHub? Open your GitHub account.
Sorry, I didn't get you. I don't know whether it was my network here.
I'm saying open your GitHub account. Open your GitHub.
Okay.
Yeah.
My GitHub.
Yeah.
I just go
Just
direct to
add,
GitHub.
just add your.
I come out of the email.
No. Let's just go to your GitHub account. Maybe add another tab and then we go to your GitHub.
Okay.
Yeah.
GitHub login. Are you able to see?
Yeah, let's see if we so that's you, yeah. So your thing Mayaba 2025. So let's go back
Yes.
to Osman's.
Go back to, is it this one?
Yeah. Where is the fork? Yeah, go to the fork. It's now down. Now down. Yeah.
Here.
There. So Mayaba owner repository. Yeah. So create fork.
Create fork. Where I do a description.
Yeah, you would if you you can just say special model or yeah, whatever. Yeah. Okay, cool. Okay. Yeah, so now we're in your GitHub. Can you see that?
Yes.
I have a Amnet. Yeah.
Yes.
All right.
Yes.
Cool.
And then Osman this side.
Yeah. So I think you can, yeah. So I think you're good to go now.
Okay.
Yeah.
So this is all what is needed in those instructions?
Yes.
No.
What else does it need, Osman?
You have to clone
Oh, cloning.
in your
his
R studio.
Yeah, in R studio.
Yeah,
So I go to R.
cloning. Yeah,
I go to R.
you open your R first. You copy the link
of
this page.
Okay. I copy the link.
You go to R, open project, file, open project.
New project, or I can use my existing?
Yeah, open new project. Yeah, new project.
New project. Okay.
And you choose Git. Yeah.
Sorry.
Can you please
we can't see
share your screen
R,
again?
man.
Oh, I can't see my R. Okay. Let me
No.
stop sharing and then go to R. Said new project, right?
Yeah.
New app.
New project. You click new project.
I don't know. I'm receiving a command that save what I was trying to work on.
Which work?
Yeah, here.
New
Version
directory?
control. No, version control.
Sorry?
Version control in the
Oh,
top.
version control. This one?
Yeah. Yes. Git, you copy your
Paste.
link. Oh, yeah. Is it the link of your repository? Yeah.
Yes, this one.
Okay, you can give the name where you want to save this project. The,
So here,
I
wait,
say
wait.
create.
and
Do
you
you, are
before,
you,
yeah,
that is,
and you are
can you
you
see where
see,
you're saving it?
Sorry?
So it says
yeah,
create,
the last step.
yeah,
You see,
create project as sub.
you see, create. No, no, not this. Before, after spatial modeling that you already, yeah, there. You
Yes.
see the link. It
Yes.
say see that
User
you want to
HP.
save this project there. Lesson.
Yes.
You already have a folder name lesson 8.
Yes.
Yeah, go ahead. Create project. No,
I
click yeah.
create.
Yeah.
Yeah.
Yeah. Running. Running. Is it okay?
Osman, are you back?
Yeah, I'm here, but we are waiting for
Osman,
Wendy.
I
Yeah.
am receiving this message.
Wow. Tena customer by
Oh,
agent
let
next.
me. I think we. Which kind of message? We don't see your screen again.
You're unable to see?
Can you?
No, we are seeing. I'm seeing the dark of it.
Yeah, you can reshare the screen.
Are you able to see?
Oh,
Yeah, we can.
cleaning total error.
Can you?
Member could not. Can you scroll right?
I think he's
Yeah,
missing G.
could not resolve host.
The
Why?
command, the command.
Oh, can you go back to your Git, please? Close
I go
this.
back to
Your
my
Git.
GitHub account.
Yeah, Git page. Yeah.
Are you there? Are you able to see?
Yeah. So go ahead to code where you are
Code here.
code. Yeah. Code. You click there. Copy this link.
Yeah.
You can, yeah, copy it. Or you can only press there where you have this. No, go
I hope
out.
it's copied all of it.
Right. Go
No, no,
to the right.
To the right, there are like two squares.
Yeah, squares.
Squares,
Yeah,
yes,
yeah.
yes.
Click there and go to your
Copied.
app.
It's copied. So
No,
go to
it's
your app.
already copied. Yeah. Go to your app.
Go to your art studio. Winnie, are you there?
Yes.
And that's your app. Okay.
Okay, let me stop sharing so that you see.
Yeah.
STA. Can you replace the link at the repository?
Yes, I've replaced the link. Let me put it again. Yeah, I've put it again. That's the new link.
Try
I
to
proceed.
create it.
Yeah.
Yeah.
Good.
Perfect.
Yeah, it's doing well.
So we are using the cron repository dashboard or R.
You can wait until it is done.
Let's finish this first. Oh, it's taking time. So for the rest, uh, is it okay for forking and cloning? Kokoda, is it okay from you?
Yeah, everyone is on the page.
Okay, good. So you can go and open the folder. Okay, it's okay now. You see Munde in the right in your files. You are in the right in the file. Yeah, you see. Good. And you also have Git in the top. It means that this project is related to Git now. In the top, where you have environment history, connection. Yeah, you see Git there. Good. Yeah. So you can open the INLA. You have this folder. You can make exploration of this. You have the project. You have the coverage. Uh, so Muinde, can you stop sharing, please? Muinde? Yeah, good. Let me share my screen. Uh, so where I am here. Can you see my screen? Kokoda, can you see my screen?
We can see your screen. Go ahead. Thank you.
Okay, so you have this folder. I think everyone has this in his computer. You have the name of the project. You have coverage. You can check the different coverage that you have here. In coverage, you see you have access, health facility, access, elevation, AV, LST day, rainfall. That's coverage. And have here the code name data prepare, where you prepare your data. You have input, where you have here a file.rtt, means that it's already run and the different variables are saved in the document .r data. So you don't have output, you have to create it after. You don't have this yet, I think. You only have this intro to INLA student R. Everyone has this script. You can open
Yes.
it. Yeah, you can open it now. We are working with this. It's going to be similar as the last session with Gloria, with Juniper, sorry, where you have a skeleton of a script and you are going to run step by step.
Yeah, we
Yeah.
like
So first,
Sorry, you said do we go to introduction to INRA?
yeah, intro to INLA
We
student.r.
click on
This
it.
is script. Yeah, we click on it and you can see from here, it can be open here. You can see this in the top. Is everyone okay?
Yeah.
Okay, you can open and you can see in this code you have first to load libraries. Here, rm list equal ls is to remove the previous running that you have here in the environment. You remove this variable. You have to bring your data. These data are already prepared in this file, data prepared. We are not using this because it is already running and we have saved the data in Madagascar clean.rdt. So you can start with this loading library and loading data. Please go ahead.
Run the
Yeah, you can run this part.
Yeah, no, the I was asking about the first one. The first time you are clearing the environment. What are we clearing?
Is it okay? Is everyone okay with this?
I don't know. So it's about line also the load input. It's not working. So,
Library raster
Are you
is
guys
showing a bit of error.
not satisfied already. What are the things you run?
So the projects that you are in.
Hello, Osman.
Yeah.
The library, when I quote the raster file from the library, it's showing a bit of error.
GitHub, can you call one by one, for example, to library INLA? Is it okay?
Okay. Library INLA, it's okay.
Malaria Atlas,
Library Malaria Atlas, it's okay.
the raster is not okay.
It's showing error. I don't know whether it's my side.
Error.
I run it again. Yes, it's showing an error.
So comment it for now. Maybe after we can check it. You can comment because I think it is only going to save files as raster. We are not calling raster file here. You can comment. You can put a JS here like this. Please.
Okay, I close it out.
Yeah, comment
Okay.
and proceed with the rest. SP tidyverse like this.
The rest are okay.
Okay. Load the data now. Are the data loaded? Or it
That
is
is
running?
12. That's 12.12.
It's okay, yeah? You have your data in this part. You have some variable
It's
up here.
saying loading required package raster.
Oh, so I think you can install
Or maybe I
In-
install raster.
raster.
Yes,
Go.
install raster.
I install?
Yes. Yeah, install raster.
Okay.
Yes, install dot package
Okay.
bracket. Yeah, you write like this. Install
Package
dot package this.
raster.
You have to
Run.
double quote, yeah, quotation.
Or quotation inside. Okay, good.
Yeah, you install.
Okay.
Is it okay in the other side? Coconut, onion?
Okay. I think that was the problem.
Okay.
So some of the people are facing errors, but most of them they were able to run this. We are able
Okay, yeah,
to-
Coconut. You can follow Harriet. You can make help if needed.
Yeah.
Yeah, I think is everyone able to run this?
No, that's the issue. Can I? Just check.
No, we are encountering some errors. Yeah.
Is it okay, Mwende?
Yes. Just a minute. Let me load data. Hey, it's giving me the same problem.
Oh,
Yeah.
why?
Raster. After I've installed raster, I go back again. I try to run it.
Yeah.
It's giving me an error.
Which kind of error?
error package or namespace, road failed for raster in load namespace.
Names. Please, can you show your
I
screen?
share the screen. Okay,
Yeah, please.
let me share. Okay, there's someone sharing already. You can stop sharing.
Let me stop it. Let me stop. It's me. I have stopped it here.
Okay. Okay. So I installed it here. You can see.
Yeah. Let me.
Yes. And then when I run this one,
Yeah.
this is the error I'm seeing down here.
Package or namespace. Well, raster. Oh. Raster was built on the. Oh. Stupid. I don't know. So maybe you can check it after. You can only flow because at the end I will give you the final script and after we can
Okay.
check about it.
That's fine. That's fine.
Yeah.
That's fine.
Yeah. You can only flow after you can run for
Okay.
yourself. Yeah. Sorry.
Okay.
Okay, good. So let me
Okay. I've
share.
stopped sharing. Are you
Yeah.
able to share there? Okay.
Yes. So I am here. I am. Yes. Okay. For other guys, can you load your data?
That team.
Yeah, that team.
The that team kept in the chat there, okay? So I think we can
Okay.
proceed.
Good. So you can flow and run this part of code where you are
This,
combining
yeah.
your coordinates, longitude and latitude, and you get your boundary with this INLA function, INLA dot is p to a segment, and you get your location. Is it okay for everyone?
Yes. Yes.
Okay, after this, we go to run with our mesh. You can run with this. We create here the mesh as we already show it in the slide. For the mesh function, you have to give your coordinate, your boundary, and you have this parameters that you can adjust. Please run this.
Good stuff. We have a song.
Is this one?
Is it okay? Is it running?
Yes.
Yeah?
Oh.
Yeah.
Okay, good. So everyone has this plot?
Yes.
Yes. Go to plots.
Okay, so
Different.
first you can see you have your border, you have your triangles, but you see here there are some cluster here.
Yeah.
In our in our slide, we say that we can add more arguments, cutoff, and the other one, yeah. So maybe you can check if you put here one, this Z.
Usman, you're muted. Usman?
It's just stuck. There's no big difference. No, I'm not big difference.
Okay. All right, I can use it.
Usman, are you there?
I put 1.5, still the same.
Still the same. Mine became empty. Yeah, it started this way. Then it changes, is it?
It was out again. Sorry. So for now, you see the change.
Yes. Nothing. It is
You see it?
minimal. Yeah, it's very minimal. It's minimal. We're still clustering.
Where do we expect to see changes? The size of the shell?
5, we 0.5, we got this plot.
Yeah.
But when
Yes.
I replace by 1, we got this plot.
Yeah, they are changing.
It's mean we reduce. Yeah, it's changed. We reduce the number of triangles, yeah.
Yeah.
But yeah, because here we have more space here. It means that we are reducing the number of triangles, vertices. But at the same time, we are creating more cluster, yeah, you see this part. So after that, you can play with that. So let's go to our here where we can add the as argument, where we can add the as argument offset and cutoff. Go ahead. Yeah, you can copy from here. You can copy this. Okay, let's copy this and go ahead to the final. Okay. And from here, we replace 0.5. We add here 1, and we can add our offset equal same 0.5, 1, and our cutoff equal up.
So you say
0.3, for example. Let's do that and run again. You see now?
But I've tested it in the
You see the change now? Yeah. So now inside we are eliminating cluster, and we are adding also an extra boundary. Only have to add here 1 Here in the marked edge, and you add this. All this come from the beginning, the mesh 0. Is it okay? Is it okay from there? You are muted. Kokoda, you are muted. I can't hear you. Yeah. Is it okay?
No, there's an issue. Are we using mesh 3?
Yeah, from mesh 3, I copy the script from mesh 0, this,
Yeah.
and in the match edge, I only add this because first we have 0.5, but I only add this, and and also these two argument.
Okay, but the mesh 2, mesh 3, and mesh 2.
No,
I mean mesh 2 and
don't.
mesh.
Yeah, mesh 2, mesh 1, mesh 2. It's only to play with the values. Yeah.
Okay.
I jump to mesh 3 in order to continue our model. Yeah, because we don't have much time.
Okay.
Yeah. Are you able to run this?
Yes.
Good. So after that, we create our A matrix. I don't know if it could not be better to share with you the slides, and because I already have the script there, or we can continue. We can continue because I see it is it is low. But
We can arrange another session.
I think Osman,
yeah,
we go through the major parts like A and SPD and ISET. We go just through the major parts, and then the where you're saying they can exercise, then you can share the slides for those.
okay. So for this, as you see, we call our INLA dot SPD. You see the function here, INLA dot SPD make. You call this function where you are adding your mesh 3. Yeah, you add your mesh 3, your location variable. You transform your coordinate as matrix, and you put your coordinates. Your coordinate here. Okay. Only you run this. It's okay.
It's bringing numbers.
Yes, it gives your dimension. You can check the dimension here.
Okay.
It's give you the dimension of the number of observation and the number of location. It is a matrix. Because you are constructing a matrix. Yeah. For matrix,
Okay.
you need the number of row and number of column.
Okay.
So after that, you construct your SPD INLA dot SPDA. You see here this function, but as we mentioned, we are using the Mattern covariance. Here we allowed to use SPD2 Mattern, yeah, as preference. We use this inla.spd2.mattern, which means that it is going to call the Mattern covariance functions that we show in the different covariance function, because you have exponential, you have Mattern, and here we are choosing this. And from this, we can give it only your mesh again, mesh A, and it has a parameter named alpha. Here we give it 2. And we proceed. Is it okay?
Are you guys following?
They are not running.
Is it running?
You run SPD.
Yes.
You have to run this. And after that, we have to define our special index called Z. For this, we still call our INLA dot SPDAE dot make. What we are making an special index, we call this. Yeah. For that, we give the name. We call here special dot field is a name, and this take another argument SPDA. From the SPDA, you can take the NSPD here. It's here. This. Is it clear?
Yeah.
And you run this also. You have your A matrix, you have your SPD, you have your exact, which means the index of your spatial. We can organize your data stack now. For that, as you see in the slide, you use INLA. All these functions are from INLA, so we start with INLA stack. Okay. For this, we first have our data. The data, we constitute a list of data where we have our y, which represents the response variable. Y equal, my data frame name is MD Z PR data, where I am going to choose my response variable, which is the PF positive plus some falsifying positive. Okay. because I need the number of positive. PFPR is the rate. Yeah, it is already calculated by PF pose divided by N. But take is the number of positive PF pose, and I have my sample size, which come from the data again. Here, it is a variable number of examined. Okay, this is my data, epidemiology data. I have my A matrix, which I constitute a list of this matrix. Is one. So one is to include uh, the coverage after. Yeah, it is only related to include the coverage after because we are making a list. So if we put in this list only one element, it's not, it haven't sense. Makes sense, yeah. And the one is related to the coverage that we are making after. So after that, we have our effect. And here we have two effects. So we make it as a list. We have our random effect that we already called Z before. And we have our covariates in a list where we have elevation,
local temperature.
Okay, we have elevation that we can find in our data. Here, elevation, yes. We do the same with access. We have this access HF equal to MDG data dollars access. We list here our variable. Yeah, let me copy to be faster here. I have this here. I have only access in my data frame. Okay, I have the other one was which one? LST day. Yeah, let me modify here. LST day is here. I have rainfall. Rain, yeah. I think it's only rain. Yeah, it's good name. Rain. Let me see rain here. And I have AV. AV. Yeah. AV. Yeah, that are my covariates in my data frame. These covariates already exist in this data frame, yeah? You don't have to create new names because it will give you an error, yeah? So after that, you can run this. Oh, what is this?
Osman, it's the bracket after elevation. I saw that. I was wondering. Yeah.
Yeah, you are right.
Yeah.
Thank you so much. So is it okay now?
Is it?
Let me see list here. And I have to add a new one, yeah, here, because here, yeah, good. So I run this. Is it okay for you?
Not yet.
Not yet. Okay. Yeah.
We are almost there. Where you able? Right, then you get the flow. Right. Just come.
Then the last one is
Yeah. EVI. Enhanced vegetation. Enhanced vegetation index. What is that? I don't know. I only know.
What he asked? What she asked?
He's asking about what is the EVI. So I told
Oh,
them I told them it is enhanced vegetation index. So
yeah.
they ask furthermore what does it mean? So I don't
Index
know.
vegetation. Yeah. It's related to vegetation, yeah?
Yeah. So what they should know it affect malaria.
Yeah. Exactly.
That's why we call it effect.
Yeah, exactly. Yeah. It is a fixed effect, yeah. Is it okay? Is everyone running this model?
Sorry.
Is this stuck?
One moment, please.
Oh, okay, good.
Windy,
So,
Windy, Windy, are you still there?
There, I'm trying to figure out the problem.
I sent you a code. Did you try run that code? I sent it to you directly via the Zoom chat.
Okay, let me check.
Yeah.
There is one more bracket for this group. For this one, clothing bracket.
This on the GitHub.
Yes. So there's a code on the chat. Try that. Try that whole the code.
in the Zoom chat, yeah?
Yeah, it's in the chat. The remotes install GitHub.
Okay, remote install GitHub. Okay.
And then your username is your GitHub username.
A lot of work is
And then
happening.
the package is Rust.
I run it in R.
Yes.
Yes, please. Is it okay from the?
Yeah. Everything is all right.
Good. So we can check here in the variable list. For example, what are the element of this stack? We can click here and you can see there are three elements. We have the A matrix dimension here. We have our data. We have our effect here. Our effect, you see, we have this. Okay. You can check after running. You can click here to check that the result is adequate or not. So after that, we can build our model. First, we can create our formula, yeah? As first formula, I propose this because we have a set of covariates. First, even if you are, for example, the question from Harriet, if you are going to make a selection of your covariates, you can try to add maybe one first. You run and you can add again until you see your how your prediction are changing and going good or not. Yeah, because you can have a indicator measure like WAC in order to measure your performance of your model. So here you need a formula. As first formula, we have a y, we have -1. Uh, it means that if you have here -1, it means that you are going to exclude our, default intercept because INLA already at an intercept, but if you don't need it, we can make here -1. And we take first elevation as primary covariates. But if you want, you can add all the list of your covariates in one time and you run your model if you are reliable to your covariate. But if not, you can check one by one. And you add your special effect here. Okay, you can run this. Is it okay? And after that, you constitute your model with the function INLA, which take your formula in first, uh, your formula, not here, formula 0, it takes it, take your data, that you already have INLA dot stack data. Yeah, because we already have made stack data. It's this function takes the stack one. How is it stacked? And it take also the SPDA. After that, you choose your family of probability distribution. Family, not the family member, but it's a family distribution probability. Yeah. Here we are choosing the binomial. The binomial distribution. We choose the number of trials, your sample size, and trials equal n. So these are the different argument in the function INLA. Yeah? You have to satisfy all of this. After that, you have some control argument, control dot predictor, which is a list of your A matrix that you already have this here. Is take your stack and you add compute equal true. Okay. After that, you have your control compute also. Control compute. Where is here? Let's take a list. Is a variable named dig equal you set up it has true. You have the web cake information criteria, which are indicator measure of your prediction. We set it as true because after fitting your model, you want to see in the summary how this model is accurate. Let's take this config parameter that we also set to true. After that, we finish by a verbose argument. So in R, you can check what is the utility of each argument when you call when you see the R markdown explanation in R. All these are set as true. So go ahead and you run your whoa. What is this? Interesting. It seems that's not an up model 0 not found. Ah, what is this error? Oh, then maybe I have this formula. Oh, it's not related to the formula. Hmm. What is this? Let me check. Yeah, I have my data. This is inla.stack.data. Let's take my stack and my SPD. I have my family. Maybe let's try with this. If I put only one quotation, maybe I have my entrials, control predictor, take a list of my A matrix, and my compute got through. I have all this. Let's see if it's work.
Usman,
Yeah,
try taking out the SPD. I don't know. I think it says something like we are repeating the SPDE. If you try running it without,
is our
where
SPD here?
yeah, yeah.
Why?
And
Oh, okay.
it ran, yeah,
Yeah,
yeah.
let
So
me check.
it was
Okay, thank you. You see, you have to check your error messages many times. Your remove is PD, but I don't know. This I run it with my new computer, but it work. Maybe it's only related to some setting with my old computer because I am using my old computer. Yeah, for the new, I didn't see my adapter. I don't know. It is low. Good. So try this. I don't know. We are running out of time. Changoro, what do you propose?
how far do we have to go, man? So
Yeah,
we've
we
run
still
the
have
model, yeah?
some step. Yeah.
We've
But
run
I
the
think
model.
I think now we have run the model and we have our parameter. So it is enough.
Yeah,
This
that is
is my
enough.
first. And the following steps are to make a selection of covariates. Here we are adding all our covariates to make selection. After this, we can make decisions that which combination of my covariates that I can use for my model. After that, I make a selection of covariate. I run the models that I have my other covariate added by
So
selection.
I think we just go with the one covariate that we have. We go to
Yeah.
validation now, and the plotting. You know, we skip the different iterations for the covariates with the different
Yeah.
for the models with the different covariates. So we just choose the elevation covariate just to show them.
Okay, so maybe let me go fast is let's wait for them finishing with the model 0 here and getting this information of parameter. After that, we can run our model with this model 0, yeah? Is it okay from that?
Yeah, we are still getting the same error even if we take off that SPDE. Maximum tries. Yeah, maximum tries.
Maximum
Try.
tries.
Maximum
Oh,
So is it which is it the one that Harriet has posted, that error?
Yes. No. Yes. It's the same error. I guess it is.
Oh, no, sir.
Yeah.
oh, I don't know. Because for me also, I didn't delete SPD in my new computer, but it works. But for this, I have to delete. So what will be
Can you run it?
Wait.
Okay, so go to we can look at this how they arrange.
I was saying here, I have something else down here. I'm gonna look at this one.
maybe you can reduce number of trials.
But it's the third one.
How many should we put there?
But your problem is
Maybe you here the n is a vector values from 1 to 6 for 7. But yeah, maybe if you reduce from 1 to 100 to see, I don't, because this is our number of observation of our data. If you reduce it, is it working?
So where did we define n?
For example, where you have n, you delete the n, you put a vector 1.1. For example, like this, you say 1, this 100. Maybe.
Still giving the same error. But it's
Harriet,
yes.
that's your error that all of you are getting.
Yeah. Yes, they're getting the same error because my error changed. The error I'm currently getting.
That's
no one. I think I'm getting.
No one can run this part.
no.
Are you getting the same number?
Maximum number of trials established.
Tumepata hiyo. Ndio ile bwana nimepata.
Oh, stupid. Yeah? It's
Guys,
stupid, yeah?
sorry, guys. Config. Did you write config or did you miss the I? Check that as well.
If you change.
You
We
changed.
have to put
For
Oh, yeah.
I tried with I, but
It's config, yeah?
Yeah, config. Right. Try run with config.
SPD.
Okay, that has solved part of the error, but still it's giving the
error.
Oh, okay, so I think
Yeah.
Yeah.
because now it's saying that there's differing number of rows.
The core? Yeah, the
Okay.
different number of rows?
It's running, so you have to change the config with an I.
Yeah.
Yeah.
Yeah, it
And
was
then-
a mistake from me. It's a config with I, yeah.
And then,
Yeah.
and then,
Just config with it's still like this one.
And after that, it works.
It's already has an I. Yeah, it's already has an I. Yeah. You put N.
Yeah, but this,
You put N.
yeah,
this
Maybe
argument.
the formula.
no, after you put the I, ikakuletea error nyingine, si ndio?
After put an I, it was saying that there's different number of rows.
Yes.
How
How-
do it's 100.
Ah,
So I returned the N and then it was able to run.
Yeah. Put the I and keep the N in the N trials.
I tried several times. It's not working.
Because my formula is.
Okay, it is here. Yes, I want it out.
It's the new meter. Can you remove it? Are your binomial in which kind of brackets?
By name.
Like which brackets? Are they the double
Ah,
brackets?
yeah, maybe.
Put one.
Yeah.
Christina, the binomial can keep the single brackets, the quotations.
Yeah, the quotation.
Single quotation.
Yeah, instead of the double brackets, and then try to
It's
write.
not.
It's not wrong.
A and aviation. One.
You can add, and yet you can replace here verbose equal false in order to not get all these messages here. All this. You can replace here by false.
Verbose.
Yeah. Because if you put true, you have to see all this running process.
That doesn't work.
Use of false, it keep it eternally. Verbose equal false.
One is to avoid the
Try
error.
intercept.
Guys, who is still stuck? Who is still stuck there?
Which it's running.
Which mechanism?
When you formula there's an intercept, you have to also remove the intercept.
After I remove the intercept.
After remove the intercept. Does the intercept in the formula also?
In the formula also.
You remove the intercept.
No, I removed the intercept because we
Yeah.
didn't create a default intercept. Remove the intercept, please.
The formula
So that was the problem.
The formula was within formula.
So
Did you run it? Run this one, I can come to run this one.
Yeah, run without.
But I know there's an issue with, can you try to run this? No. Unexpected echo sign, where is it? This one.
Is it okay?
Yeah.
It works, yeah?
Yes.
Okay.
That's sort of very convincing. Yes. Who is still stuck?
So after running the model, you can check in the summary here your coefficient. You see here you have this elevation coefficient for the fixed effect. You don't have here an intercept. If you want to include the intercept, you can change here plus. Go ahead, change here plus in the formula and run again.
This one plus this one.
Yeah. For the -1, you can change +1, and you can check now for our, you see there is an intercept here.
Check your suffering. Fibers. Check your suffering. And try that so because you set tables. Tables you set was if you want to display these things. You don't want,
Is it okay?
you don't want the information.
It's okay.
Yeah. It's all right.
We can
Everyone is okay?
we can jump. We can
Don't tell
you
them
can
about it.
run this part. Please don't run this part because it takes time. It is ready for selection of variables here. You can run it because I will share the final code. We go after getting our model, we can uh, make the prediction. So we are using the same formula defined before. You can, you, what is this? We can comment this. We are not interested to this formula. And for our model, we still use model 0 defined before. We don't run this part also. We jump. Maybe we can check our parameter distribution here by changing here model 0. Go there to change. For example, if we change the model 0, we run this. We see here we have our beta 0. Here I have only changed here this first because it was running with model 1 that we didn't run here yet. We still keep the model 0 that we run before, and I replace here the 1 by 0, yeah. And I only take one as a coverage, which was elevation, I think. So I need to copy this elevation here and put it here. Okay. So I am interested only for this elevation. I replace the 1 by 0, and I only want to show the regression parameter of this intercept and elevation. So here I want to uh, divide my window. I think I can say that I want 2 line, 1 column. Yeah, for the MF row, it divide your window. If I run this, where is the second? Oh, let me. Oh, what?
Did you run the elevation? Did you run float model elevation first? Oh.
Oh no. Let me check it. Oh, it's number 2. Yeah, it's related to the position. It is because we have 2 parameter. You see here.
Yeah.
we have my two coefficient here. It is beta 0, and here is the elevation regression coefficient. Okay. After checking with this, I go to the model prediction here, please. Sorry. First, I define my reference image. Okay. I country location, reference coordinate, and I make prediction point, coverage list. I have this. So what I am going to do is to replace this. So let me go to the final one and go fast. I'm here. I will share with you this. Yeah. I'm here. Model one. No. Yeah.
Yes.
I still keep the mesh 3, and I have my reference coordinate. Can make this. I can check. So you see now how is the number of points. These are the pixel point here. These are the pixel points. First, in your data, you have number of observed point where you have data, but after making the mesh, your model give you pixel point in the whole country. It's bigger than your data point, but after you are aggregating where you have only data. So after that, I make prediction. Let me see if so. Here I only took elevation. Let me comment this because I am running my first model. I didn't include this. Yeah, and then the AV. Oh, yeah, let me do this. Okay, let's run this. Oh, what is this?
Your brackets.
Yeah.
So double bracket at the end. Tag, after tag,
Yeah.
put another bracket. Tag.
Tag.
Yeah, try another bracket there. Is it?
Like this?
Yeah, try run.
No, it's not related to the bracket, I think. But it say that elevation argument 2 is empty. Oh yeah, this is a comma here because it expect another argument, but I didn't give it the argument. So I run this. Okay, after that I join. Okay, and what is the following? Is it yes? Let me. I am running the formula 0, and all the rest is okay. I think yeah. It takes time, but yeah, it's okay. So I have my prediction index. Mean. Okay, and I have this logistic path regression. I define my graphics. Okay, I have this background. Let's do this. Yeah, We have the prediction here from one covariates here. Here are the prevalence values here. You see they are between 0 and 1. You have your maps. And it means that you have your Madagascar map, and you see in some part you have your high values. In another, you have your low values. It means that where we have the green color means that where the prevalence is higher. Is it okay? Everyone has followed? At least one from you? Harriet, where you are? I see you are not okay.
Nobody is following.
No, everyone is.
Let's
Did everyone get this? Anyone?
No.
Okay. One moment, we are waiting on this plot here.
yeah. Are you there? Prediction option 1. Go to prediction option 1.
Not
Is it okay?
Maybe I will go back to line 227.
Line 227.
227.
Yeah.
Which means this
No.
before, after this.
Yeah, 227. Go down.
You are talking as if it's you.
Osman, can you go to line 227?
Are we muted? We are muted. But I'm going to
You're able to add. Oh, you're able to add.
I may add.
Yeah.
So what is it? What is the method?
No, it gave error. And I think it's because the standard. I just added these ones.
The A prediction.
Yeah, the predictions is where I stopped.
Yeah, feel like they may switch you sure. Sure not to. Location. Location, I think, is related to coordinates. Find somewhere you created the coordinates. So is Osman still there or is gone?
It's not there.
Oh, it's Angoro.
Yes. Yes.
Yeah, we are waiting. I don't know Osman has the internet problem.
So where were we? So he has the slides. Bollocks.
It's until you slide.
This one a prediction.
So
Print comes, they're not found.
So have you guys managed to get the prediction maps?
No, not yet.
What is happening?
It is where we are waiting to ask.
Where are you stuck? What is the error?
Hey, what is the error?
I guess getting the error.
Everyone is getting different error. You can mention one.
So even I was getting an error. So the problem is, you remember creating the structure.
Yeah.
Yeah, it can tell you the number of effects are 3 and the length is 2 and stuff like that. So that is a basic error where you just it's how you create the structure. So probably the commas and all. Just a minute. Tell you, Osman.
Let's try.
That's complicated, so scale reduction data. If effect is
It's maths.
account is for
We have created different dimensions. The structure is different from what the model has been learned. As the model learns the different here. Try to see. Try to run the next one.
So,
Okay, fine.
we are trying the mesh.
Did you try one?
Mesh one is not found.
You didn't create mesh one.
I have zero.
Which formula is formula 0? Formula is formula 0.
Yeah.
Where do we put that from?
Yeah.
Mine is running.
It's running. Oh, that's right.
So you can plot.
Okay.
I hope it plots.
Share your
When
screen.
you A prediction,
I predict
mesh
mesh 1. Okay,
Mesh
mine was
one.
mesh 1. It was mesh 3.
It
not
is the
mesh
one
1.
which is telling you
And then you
yeah,
have
it's not found.
mesh equals to mesh 1.
location.
Yeah.
Reference dot coordinates. You have to run the easy line inside you.
This is a new design here.
But do you have reference coordinates?
Huh?
Hey,
You have
hey guys.
Yeah, there is.
Oh, yeah, maybe.
There is.
Hello, guys.
Yeah, we can hear you.
Yeah, so Osman is saying he's having trouble connecting back.
Yeah.
So we first thing first, we have to reschedule for another 30 minutes because I don't think it's going to be very fruitful if we go on and you guys are having errors and you're not able to create the stack. So the issues that you're having in creating the stack, like I said, are just structural issues. So maybe you've lined up the covariates have a different number than the spatial effect. So this needs a lot of debugging to get the stack correctly, the structure correctly. I don't know if you understand how I mean.
Yeah. We
Yeah.
can
So we will do that. We will try. So in that session, we'll try debugging the issues that most of the errors that you guys are having, so that it will help us also when you're working by yourself to see how you can go ahead and debug your own errors and create the stack. Yeah.
Exactly.
So that is one thing. So I'm going to propose a new date. I'm just going to look at the calendar and then I'll text you guys. We'll maybe do a poll on WhatsApp and see when we can have the 30 minutes. Secondly, you guys need to fill in the project Excel sheet. Yeah?
Yeah, we already filled.
Everyone already filled?
I already filled.
Has everyone done that? So if you have done that, maybe if you do that, then maybe you can text just on the WhatsApp so that I know you have filled that. So we need to also have a meeting to pick the projects, to group you guys in the projects.
Only one person left.
Yeah? Say that?
Only one person hasn't filled yet.
Only one person. Who is this?
The Emma, and she's not around.
She was around.
She was around. She's so bad.
You can text her that. So we are going to propose a meeting for forming the groups.